I wanted to work through the practice test. Question number 1 begins with, determine the direction of the magnetic force on an electron with a velocity v and in a magnetic field as shown below. So this is a case of the right-hand rule. And in the right-hand rule, you're going to point your palm of your right hand in the direction of the velocity vector. So in this case, it's upwards on the page. And you're going to curl the fingers of your right hand in the direction of the magnetic field. And that means I've got to turn my hand over and point my thumb into the paper so that I can curl my fingers in the direction of the magnetic field. So they're curling towards the right. So my thumb is pointing inwards. So I denote that with a cross. That would be the force on a positive particle. Now in this case, we've got an electron. So the force on the negative electron is in the opposite direction. So that would be out of the page, denoted by this dot here. Second question. So second question says we got two equal mass, equal charge particles, and they're undergoing circular motion in a uniform perpendicular magnetic field. And we're told that the radius of the orbit for particle 1 is twice the radius of the orbit for particle 2. And we've got to compare the speeds of the particles. Now, in a uniform magnetic field, moving charged particles execute circular motion because the magnetic force in the magnetic field provides a centripetal force that causes the circular motion. And that enforces a relationship between the velocity of the particle and the radius of the orbit. And that relationship, let me write it down. Is this one here. So in this equation, Q and M are the properties of the particle. So the charge and the mass. And in this case, the two particles have the same properties, same charge, same mass. B is the magnetic field. In this case, the two particles are in the same magnetic fields. And so this just tells you how, the radius of one particle's motion is related to the velocity of that particle's motion. And the radius of the other particle's motion is related to the velocity of the other particle's motion. It tells you that the velocity is in proportion to the radius. Since R1 is twice R2, then V1 must be twice V2. The radius is twice as big, the velocity is twice as big. So question number 3. Question number 3 is about the force and the torque on a current loop in a uniform field. And the particular geometry is that the field lines are parallel to the surface of the current loop. In this drawing, the field lines are in the plane of the page, and the loop is in the plane of the page. And we've got to figure out the net torque, whether it's zero or non-zero, the net force, whether it's zero or non-zero. The equation that we'll use as we do this, let me just write it down. is the force on a current loop, force on a current carrying wire. It's this equation here. So I is the current, L is the length of wire, B is the magnetic field. Theta is the direction between the current and the magnetic field lines. And this will tell us the force on the different parts of the current loop. So I'm going to break the current loop down into 4 pieces: the top, the bottom, the left, and the right. For the top, the force is going to be 0. That's because the current and field are in opposite directions. So it's sine of 180 degrees. That's going to be 0. On the bottom, the force is 0. That's because the current and field are in the same direction. A sine of 0 degrees, that's going to be 0. On the left and right, well, on the left and right, there will be forces that are determined by the magnetic field and determined by the current. Those forces, since the current is perpendicular to the field on the left and the right, will both have a size that is just ILB. So I'm just writing down the size here, not the direction. But what's going to be most important for us is the direction. And the direction we can again get by the right-hand rule. So you want to point your palm of your hand, right hand, in the direction of the current and curl your fingers in the direction of the magnetic field. So on the right-hand side, that tells me the force is inwards. On the left-hand side, that's telling me the force is outwards. And so we do have 2 forces that are acting on the current carrying loop. And those forces will determine what torques occur on the current carrying loop. So firstly, let's do the total force. The total force is going to be 0. Total force is 0 because there's a force of ILB out of the page on the loop, and there's a force of ILB into the page on the loop. So they're equal in size, opposite in direction, they add up to 0. The torque will be not 0. Think about this axis. This force, outward force on the left-hand side, will try and twist the loop out of the page on the left and into the page on the right. That's the torque that would be made by that force. The force on the right-hand side, that's going to do the same thing. It's going to try and push the right-hand side of the loop into the page and pull out the left-hand side of the loop from the page. So they're both turning the loop in the same direction. And so the 2 forces that add up to 0 to make 0 force actually add up to make a torque that's non-zero. And that's why this is the situation where the rectangular loop will rotate in the uniform magnetic field. Okay, question number 4. Question number 4 says we've got an inductor resistor circuit with a battery and a switch, and we're told we close the switch at time 0. And we're asked to consider the case where we double the inductance. So if you double the inductance, what happens to the time constant for the current building up in the circuit? And what happens to the final current that's flowing in the circuit? Does the time constant change? Does the final current change? Well, let me write down a couple of equations. So the time constant of the circuit, that is dependent on the resistance and the inductance. It's the ratio of the inductance to the resistance. So if we increase the inductance by 2, but we don't change the resistance, the time constant is going to be twice as big. And so it's going to take twice as long for the current to build up. What about the final current? The final current in the circuit is determined by the EMF that drives the current around the circuit and the resistance of the circuit. So that's epsilon over R. Well, we changed the inductor, but we didn't change the EMF, and we didn't change the resistance. So the current is unchanged. And so it took longer for the current to build up, but the final current is unchanged. Okay, question number 5. Consider a solenoid of radius r, length L, and turns N. Doubling the length of the solenoid, but keeping the radius the same and the turns the same, does what to the inductance? So we've got a solenoid. We know the geometrical parameters of the solenoid, the radius, the length, the number of turns. And then we're going to double the length of the solenoid, leaving the other quantities unchanged. And we're going to comment on how the self-inductance changes. Well, this is a matter of looking at the equation for the self-inductance. There's actually 2 ways you can write it, 2 ways you'll see it written. Let me write them both down. This is one way you can write it. Mu naught times the number of turns of the solenoid squared times the cross-sectional area of the solenoid divided by the length of the solenoid. The other way you can write it is this way. This is mu naught times the number of turns per unit length of the solenoid times the area of the solenoid times the length of the solenoid. Let me make that a squiggly L. So you have to be careful with these 2 ways of writing the inductance of a solenoid. In the one on the left, it's the number of turns, uppercase N. In the one on the right, it's the number of turns per unit length, lowercase n. And they differ in that you divide by the length of the solenoid and multiply by the length of the solenoid in those 2 cases. Now, I'm going to use this one on the left because we keep the number of turns the same. And so if I look at this equation for the inductance, what happens when I double the length? Mu naught doesn't change. N doesn't change. A doesn't change. Only L changes. And if L doubles, then because it's in the denominator, L will halve. So when L goes up by 2, then L, the length, goes up by 2. The self-inductance L is divided by 2. Okay, question number 6. Consider 2 beams of light. The amplitude of the electrical field in beam 1 is 2 times the amplitude of the electrical field in beam 2. How do their intensities differ? Well, the intensity of a light beam, which is, if you remember, the number of joules per second per square meter of energy that's carried by the light beam, that's proportional to the electrical field squared in the light beam, or it's also proportional to the magnetic field squared in the light beam. So that means if the electrical field is doubled, it goes up by a factor of 2, then the square of the electrical field is going to quadruple, which means that the intensity of the light beam will also quadruple. And so the intensity is 4 times bigger if the electrical field is 2 times bigger. Okay, question number 7. A proton moving at 6.8 times 10 to the 6 meters per second through a magnetic field that is 1.72 Teslas. And there's an angle of 45 degrees between the field vector and the velocity vector. We've got to calculate the magnetic force on the proton. Well, this is a job for our equation that describes the magnetic force on a moving charged particle. So it depends on the charge, it depends on the velocity, it depends on the magnetic field that moving charged particle is moving through, and it depends on the angle between the two vectors involved, the velocity vector and the magnetic field vector. So to solve this, we just have to plug in the charge of the proton, 1.6 times 10 to the minus 19 coulombs, the velocity of the proton, 6.8 times 10 to the 6 meters per second. The field that it's moving through, it's 1.72 Teslas. And the sine of the angle between the direction of the field and the direction of the proton. So it's sine of 45 degrees. And if you multiply all those quantities, I computed it over here, I got 1.3 times 10 to the minus 12 newtons. 1.3 piconewtons. Okay, question number 8 says we got a 0.5 meter straight wire carrying a current of 2.5 amps and is placed in a magnetic field of 0.3 Teslas. And the wire is perpendicular to the magnetic field. So what's the force on the wire? Well, for this, we're going to use the equation for the force on a section of current carrying wire. And that equation is that the force equals the product of the current times the length of the section of wire times the field that it's immersed in times the sine of the angle between the field and the current direction. So in this case, the current is 2.5 amps. The length of the wire is 0.5 meters. The field is 0.3 Teslas, and it's the sine of 90. So that's 1. So we got 2.5 times 0.5 times 0.3. That's 0.375. And those units are going to be the units of force. That's newtons. So 0.375 newtons is the force on that section of wire in that magnetic field. Okay, question number 9. A long straight current carrying wire carries a current of 0.5 amps in the positive Z direction. Calculate the magnitude of the magnetic field at a radial distance of 12 centimeters from the wire. So this is a question about a magnetic field of a long straight current carrying wire. So we met some equations for magnetic fields of current carrying arrangements, loops of wires, straight wires. And the one for the straight wire is that the magnetic field B equals mu naught over I divided by 2 pi r. Now, in this equation, mu naught's the magnetic permeability that characterizes the strength of magnetism. I is the current in the wire, and r is the radial distance from the wire. So if we fill in these numbers, we've got 4 pi times 10 to the minus 7. That's the permeability. We've got a current that is 0.5 amps. We've got to divide by 2 pi times the radius of the wire. Sorry, 2 pi times the distance from the wire. That's 12 centimeters or 0.12 meters. And if we plug all those things in, I've already worked this out. I'm looking for the answer here. I get 8.3 amps. Number 10. Number 10 says we got a solenoid. Its length is 0.64 meters. Radius is 0.025 meters. It has 1,200 turns and generates a 0.02 Tesla field. We've got to find the current in the solenoid. Well, this is another important configuration of a current carrying wire, a solenoid, and there's an equation for its magnetic field. You might remember it. It's this one here. The magnetic field in the center of the solenoid is mu naught times the number of turns per unit length of the solenoid times the current that's flowing in the solenoid. Now, in this example, we want to figure the current knowing the field. So we've got to rearrange this equation, divide through by mu naught, divide nu through by n, and then fill in the field, 0.02 Teslas, and fill in mu naught, 4 pi times 10 to the minus 7, and fill in the number of turns per unit length. Number of turns per unit length is 1,200. That's 1,200 turns divided by the length. So that's 0.64 meters. And so plug in all those numbers and we're going to get the current. And I calculated the current to be 8.49 amps. Okay, number 11. A square coil with 12 turns and cross-section 2.4 square centimeters rotates with angular frequency 377 radians per second in a 1.75 Tesla magnetic field. Calculate the magnitude of the induced EMF in volts. Well, this is a problem about induction. We've got a moving coil in a magnetic field, and that creates a induced EMF by Faraday induction. And that induced EMF depends on the number of turns of the coil. It depends on the cross-sectional area of the coil. It depends on the magnetic field the coil is moving in. And it depends on the angular frequency that the coil is rotated at. Now, it also depends the EMF, induced EMF at any moment, on the sign of the angle between the coil and the field. But in this case, we're asked to consider the maximum induced EMF. And that maximum induced EMF is when that angle is 1. And so we're just going to be using this equation here. And all we've got to do is fill in the number of turns, 12. The area is 2.4 times 10 to the minus 4 meters squared. The frequency and the field. So field is 1.575 Teslas. I'm running out of space, I won't put the units. And the frequency is 377 radians per second. And if we multiply all those things together, we get the maximum induced EMF. And that maximum induced EMF that I got was 1.90 volts. So that was an example of an electrical generator creating an induced EMF by rotating a coil of wire in a uniform magnetic field. Okay, question number 12 is about a solenoid in which we're changing the current over time. We're told the parameters of the solenoid. It's got 455 turns, it's got a length 8 centimeters, and it's got a cross section that's 2.9 times 10 to the minus 5 square meters. And we're told that the current in the solenoid goes from 0 to 3 amps in 7.8 milliseconds we've got to figure out the induced EMF in the solenoid. There's a change in magnetic field in the solenoid, so there's a change in flux through the solenoid, so there's an induced EMF in the solenoid. And we're going to work out this problem in those three steps. First, find the change in magnetic field. Second, find the change in flux. Third, find the induced EMF. So let's do that. The change in magnetic field is actually the final magnetic field. That's because we've got a solenoid that was off and then turned on. And so the change is actually the final field. And for a solenoid, that's mu naught Ni. And all these numbers we know, 4 pi times 10 to the minus 7 is mu naught. The number of turns per unit length is 455 divided by 0.08, the length of the solenoid. And then the current in the solenoid is 3 amps. And so we multiply all those things together, it's going to give us the field. I got 0.021 Teslas. That's the magnetic field. That's the change in magnetic field. What about the flux, the change in flux? Well, the change in flux is the final flux because the initial flux was 0. The flux through one turn of the solenoid was the field in the solenoid times the cross-section area of the solenoid, but there are n turns in the solenoid, and so it's NBA is the total flux change in the solenoid. We've got 455 turns. We've got a field that's 0.021 Teslas. We've got an area that we were told is 2.9 times 10 to the minus 4 square meters. And if I multiply those quantities together, I get, I got 0.28 milliwebers, 10 to the minus 3 webers. Finally, the EMF. The EMF is the change in flux divided by the elapsed time. The magnitude of the EMF is the change in flux divided by the elapsed time. Well, the change in flux is 0.28 milliwebers. The elapsed time is 7.8 milliseconds. And so 0.28 divided by 7.8 is equal to 0.036 volts. And so that's the induced EMF in a coil of wire. Okay, question number 13 is calculate the inductance of an inductor in millihenries if it stores 0.0025 joules when carrying a current of 1.9 amps. This is a question that's about the relationship between the potential energy in an inductor and the current that's flowing in the inductor. And this is that relationship. The potential energy is half the inductance times the square of the current. Now, in this particular problem, we want to find the inductance, knowing the current and the stored energy. So if we multiply this equation by 2 and divide by the current squared, we're going to get that the inductance is twice the potential energy divided by the square of the current. We can plug in the potential energy, 0.0025 joules, plug in the square of the current, that's 1.9 amps squared. And if we multiply that out, we get, I'm looking it up right now, trying to find it. I got 0.1 139 millihenries. And so that's the inductance of the inductor, derived by knowing the energy it's stored and the current that was flowing. Okay, in question 14, we're asked to figure out the maximum electrical field in volts per meter in sunlight at the top of the atmosphere, having been told that the intensity of sunlight at the top of the atmosphere is 1,360 watts per square meter. And so this is a question that involves the relationship between the electrical field, the maximum electrical field, and the intensity. So I is the intensity, E subscript M, the maximum electrical field. And these are just constants, proportionality constants between the intensity and the square of the electrical field. In this case, we want the electrical field knowing the intensity. So we've just got to rearrange this equation. So I'm going to multiply through by 2 and mu naught and C. And I'm going to take the square root to get the equation for the electrical field in terms of the intensity. And so that's this equation, just rearranging the relationship between intensity and electrical field. And then if I plug in all the numbers, I'm not going to write them all in. 2 times mu naught, 4 pi 10 to the minus 7, times c, speed of light, that's 3 times 10 to the 8 meters per second, times the intensity, which is 1,360 watts per square meter, you'll get an electric field. I got 1,012 volts per meter. Okay, final numerical answer question. Question number 15, calculate the wavelength in meters of an electromagnetic wave that has a frequency of 88.1 megahertz. So this is a question about the relationship between wavelength and frequency and speed of a wave. And for light or other electromagnetic waves, this is a radio wave, the speed of light is equal to the wavelength times the frequency. You can see that this is dimensionally correct, right? The speed is meters per second, wavelength is meters, and frequency is per second. Now, we want, in this particular case, the wavelength knowing the speed and the frequency. So we just divide through by the frequency and then fill in the speed, 3 times 10 to the 8 meters per second. Fill in the frequency, 88.1 times 10 to the 6 inverse seconds. And if I calculate that, I've already done it, I got 3.4 meters. And so that's the wavelength of an electromagnetic wave that has a frequency of 88 megahertz, 88.1 megahertz. Question 16 asks us to consider a proton that is moving with a certain speed, 6.5 times 10 to the 6 meters per second, in a certain magnetic field, 1.38 Teslas. And the first two parts of the question about the proton are, we're going to find the maximum value of the magnetic force that could be exerted on the proton, and we've got to find the magnitude of the maximum value of the acceleration of the proton in that magnetic field. So let's do those two parts, then we'll talk about parts C and D after that. So the starting point for this problem is the magnetic force that's exerted on a moving charged particle when it's immersed in a magnetic field. And that equation is that the magnetic force on a moving charged particle is the product of the charge of the particle, the velocity of the particle, and the magnetic field of the particle, and the sine of the angle between the two vectors that are in the problem. One is the velocity vector of the moving particle, and one is the magnetic field vector describing the magnetic field. So that's the force on a moving charged particle in a magnetic field. The maximum force occurs when the motion is perpendicular, right angles, 90 degrees to the magnetic field. So that's when the angle is 90 degrees, sine of 90 degrees is 1. And that's what we're going to consider here. So the maximum force is just the size of the charge times the speed times the magnetic field. And all of these quantities we know. So a proton has a charge 1.6 times 10 to the minus 19 coulombs. This proton is moving with a speed 6.52 times 10 to the 6 meters per second. And this proton is moving in a magnetic field that's 1.38 Teslas. And if I multiply those three quantities together, I mean, the charge is very small, the speed is very high. We're going to get, in the end, a very small number because the charge of a proton is so small. I've worked it out here. Let me find it. I got 1.4 times 10 to the minus 12 newtons. So that's that tiny force, maximum force that could be exerted on that proton. So that's the answer to part A. Part B. Part B is about, well, what acceleration does that force cause? So what's the maximum acceleration? Let me put a little subscript M on acceleration due to this maximum force. Well, all we have to do to solve that is to turn around Newton's second law, or F equals ma, that relationship between the force that creates the change in motion and the change in motion, the acceleration itself. And the acceleration, the maximum acceleration, will be the maximum force divided by the proton's mass. And you see here, right, more force makes more acceleration. More mass or more inertia would make less acceleration. Now we know the force, 1.44 times 10 to the minus 12 newtons. We know the mass of a proton. Well, I mean, I had to look up the mass of a proton. (1.67 times 10 to the minus 27. So I'm dividing the force by the mass. And if I do that, I'm going to get, this time, an enormously large number. I'll go look it up again. 8.6 times 10 to the 14 meters per second squared. So that's the proton's acceleration, maximum acceleration. Parts B and C. Parts B and C ask us now to think about not a proton moving with that speed in that field, but an electron moving with that speed in that field. So what's the force on the maximum force on an electron rather than a proton? What's the maximum acceleration of the electron rather than proton? Now the question is just asking us to say, are these things the same or are these things different? So let's start with the force, the maximum force on the electron. Well, it has the same size charge as a proton. They're both 1.6 times 10 to the minus 19 coulombs. It has the same velocity as the proton. They're both 6.52 times 10 to the 6 meters a second. Has the same field that it's immersed in as the proton. And so the maximum force for the electron, which is its charge times its speed times its field, is going to be the same as the maximum force for the proton, because it's the same charge, the same speed, the same field. So force is the same. On the other hand, the proton is much heavier than the electron, or the electron is much lighter than the proton. So although they both experience the same force, the heavy, relatively heavy proton will experience much less acceleration. The much lighter electron will experience greater acceleration. So this is larger. And so that's the answer to problem 16.